If you're having a sense of déjà vu, that's not a coincidence. We're doing a redo of the last stream, which you probably haven't seen, so that's totally fine. Today's topic will be actually two different topics, and for the first one, the potentially longer one, we're gonna start with some sample code. I'm just gonna make an array here, string array, words. Gonna fill it with some words, with the classics, like so. And now I want to render those words individually in the console. I want to write them out, the content of this string array words. For that, I'm gonna just have a simple loop and go through each item in there and use a console write line to write them. But because I'm potentially gonna output some more arrays, I'm gonna write a specific method for that, so I don't have to rewrite the entire array loop every time. Static void. Oh, right. Let's call it that. And it will get the string array. And then we're gonna have a simple loop. 0, less than. Actually, let's do the for each. That's what we learned it for. For each string word. Oh, that's item. In array. Console.writeLine. And now let's make it a bit more fancy. Dot write line that items in array like that, and then for every line after that I'm gonna use interpolated string. I'm gonna write out the word after a tab. We'll get back to that in a moment. So like that should be it, and then we can call it write words like that. This syntax here, we have first a backslash, not a forward slash, don't get confused with that, backslash. And backslash means, hey, the next character after this has a special meaning. Don't treat it as just text. It has a very special meaning. Just like in our case, we have an interpolated string, so these curly brackets have a special meaning. You can have special meaning for other items as well. And in our case, we want the special meaning of the letter T, which just means, hey, in this place where we have this backslash T, place in a tab. Okay, that doesn't quite work like that, but if you see the white space in front, that's one tab. That's 1, 2, 3. Okay, I guess on this editor it's equivalent to 2 spaces, but yeah, that's just to indent a line of text a bit. So if I output this now, we have our normal line items in array written directly, and the items themselves are indented so we can distinguish what was just normally written and what was inside the array. Just a little indicator what was what. Now let's do the same, but with a different array and numbers. See, 2, 3, 5, 7 classics like that, and I want to write out numbers. That's a bit of an issue right now, because write only accepts a string array. Can't do that for an integer array. To do that, we have to create a new method. Actually, let's output the old one as well. Words, we keep that. And we want a second one that accepts an integer array. And we write out again items in array, and then we have to iterate through the array. Again, integers. And because it's an interpolated string, we can just leave it as is. We'll just convert the integers into strings automatically and put them in the output. So if we run this, we get the first array and the second one. And let's do one more. Oh, float. More numbers. Let's see. 1.41, 2.78, 3.14, yeah, for example. And I want to do another write for more numbers. And that means I have to copy this method again and change the type to float. I can leave the rest of the code as is because that works the same. But I have to adapt a few things here and there. And then... what did I... Oh, okay. Should have used double. I have to specifically tell the system that this is not double. Right. The default type for decimal numbers is in C# a double, not a float. So I have to use the little indicator here that it's actually a float. But yeah, this works. 3 different arrays with values that I can write to the output using 3 different methods. And you can imagine this getting kind of tedious when I introduce even more different data types that I want to output on the console. Because every single time I would have to add a new method for that specific data type. Of course, all I have to do actually is just copy and then replace the data type, which only appears twice in the entire method, with the actual data type I need. So it's not too much work, and a simple copy and maybe a string replace would work just fine. But it's still extra work, and it takes up a lot of space for basically the same functionality. And because this kind of situation happens a lot, and for other reasons, there's a feature in C# to avoid writing this method several times yourself. It's a way to let the compiler do all that work for you. And the way that works is by telling the compiler that a specific method you wrote once is actually a kind of template that it will just copy as many times as needed for every single type of data you feed into it. For us, we have 3 different calls to write. One with strings, integers, and floats. And so the compiler should create 3 different methods for us, for a method called write that accepts a string, int, or float array. The way to do that is to write our method as usual, but then we mark it as a special templating method. That's not the official term, by the way, it's just to give you an idea what this is actually doing. And to do that, we add these angular brackets behind the name, but in front of the brackets, the normal brackets for the parameters. And inside these angular brackets, we give it a name for a data type that doesn't exist. I mean, technically I could actually write a program that is a type that exists, but that's very confusing and leads to other issues. What definitely does not work is, for example, putting a string in here, because that's a reserved keyword for a data type that already exists. Usually there are some default names you would use. The most classic one is just T, an uppercase T. It's a fictional data type now that within this method is accepted as a type of data. It's as if when we write this method now, the rest of this method, after this declaration, as if there's a class somewhere or a struct called T. So we can use that as an actual data type now in here. Again, it doesn't exist, we just pretend it exists. And we do that in here as well. And because it doesn't really exist, the compiler knows exactly what parts of our code are actual data types we want to use every single time we use this method, and what parts of this method are to be replaced with the data type we need in that situation. So with this, the compiler knows we have a generic method write. That's the actual term. It's generic, it's not a specific method. It's very generic. It's not for one type of data, it's for every kind, sort of. The compiler knows this is a generic method, that it can accept an array of any type, and we see there's a method called to write 3 times for 3 different data types. So the compiler knows we have to actually have 3 different copies of write in here. I'm not gonna bother with adding them all. And every time it makes a copy, it has to replace the T, the fictional data type we placed, with the actually required data type. So first one for string, it replaces our fictional type with an actual string, specific type. And then it makes another copy where it replaces the T with a integer, and so on. And this original method we wrote, that doesn't exist, sort of. Again, it's a bit iffy and I'm not too clear about the details, but basically this is just us tell the compiler what the method would look like, and the compiler will create 3 actual methods for these 3 different method calls. And if we have... Oh, actually, let's first see if it's running. It's still running, with only one write method. And if I add a 4th integer, 4th array, let's do a boolean. True, false, false, true. Like that. We can just call the write method without writing any new methods down here really, and the compiler will add the 4th one automatically based on our template, so to speak. Again, not the official term, that's just easier to understand, I think. This is not a generic method, this is a template for a method that works for every single data type we put in as array, including custom ones. So I can actually make this program, even though that's not too smart to do, but we can do this. 2 instances of program, which don't really do anything because we only have static methods in here, but those are valid instances and we can output that, which also doesn't do much because an instance of program converted to a string will just give us the name of the type, which is program, but it does work. And that's the power of generics. It's a way for us to limit how much code we actually have to write, which means there's less code overall, making it easier to read. It also means that any error that might sneak in is only in one location and easy to fix and easy to find, because every single instance of that method will cause that error. So if there is an error, you will basically always see it. Might be a simple typo, like just item. Well, it's wrong in everywhere, so just correct it in here and done. Or it might be something a bit more sneaky. You will see it occur, basically guaranteed, and it's easy to fix. This concept of generic data types has a couple of limits. Because T right now could be anything, it also means we can only use code that will work on everything. For example, in our case here we have int and float, which are basic data types, just numbers, which are copied directly, structs, if you will. But string and program are reference types. What we have stored in here are only addresses to parts of the heap where the actual data are stored. That means if we check the value for certain properties, it might have them, it might not have them. In the simplest case, checking if something is null. If we have a reference type, for example, and we pass on a null, well, this code will work because the interpolated string is fine with that. It can deal with both types, but there are things that cannot work. For example, if I try to just check if... Okay, this is not good code because we are assuming that at least one item exists, but if I do this to check if an item is null, let's just do it like this. it doesn't make too much sense in the context of value types for numbers or more numbers. This, of course, it's not null. It cannot be null. At least in this case, it still compiles, but not every piece of code will compile. Not sure how to... I don't think there's a very easy one. Did we have an easy example of something we did in the past that could not work now? Can't think of something right now. Anyway, not every piece of code will work. And so sometimes you want to limit what this T can actually be. We don't tell the compiler everything is allowed. We tell it only use this template, this generic method, for specific types of data. So we can have a limiter here, T, like so, that tells the compiler, accept this as a generic method only when T is something else. It's always this keyword where, the name of the generic data type, T for us, and then a colon. And these filters, these conditions, they are called constraints. There are quite a lot of constraints in newer versions of the language. We're currently limiting ourselves to version 7 forcefully, because that's what this compiler actually can do. Not even 7.3, which is disappointing, but anyway. In this version, the only real constraints we have are 4 different types. One would be to limit it to only class, which means limit T to only reference types. So it would work for words and truth. Actually, let's rename this, because that sounds pretentious. Let's do it like this. The compiler should now complain about these two, because they don't fit this constraint. Must be a reference type. We can do the opposite as well, where we limit it to struct, to value types. So programs and words don't work anymore. Then there's a fourth one. This one is a bit weird. The fourth one limits the T, the type of T, to be something that can be constructed. So it has to be a reference type, but it has to be you have to be able to construct it using the default constructor. So without any keywords or without any arguments. We do that with this, just a new and empty brackets. And that's just the way to write it. There is no new strings like this. That doesn't exist. You can't limit it to something with a specific set of parameters, only to this. And we can create a new string like that, for example. Well, actually we can. I'm curious, I'm not sure if they allow that. I mean, program will definitely work. But, okay, string doesn't work. Well, we learned something new. Yeah, program would be just fine, because we can create a new program, obviously, with just a parameterless constructor, the default constructor. This would be quite useful, because now I can actually do t equals new t, like so. That's a good example. This I can do now. Let's comment those out, so the compiler doesn't complain. So we can do this just fine. The compiler accepts it, because it knows T can be called with the constructor without parameters. If I were to remove this constraint and allow any type, ignore the warnings, this is the one we care about, the error. It specifically tells us it doesn't have the constraint. We know more than that. It's even so that it doesn't actually work for all these types, but that's what you can do with constraints. Oh, right, forgot the last one. This goes back to inheritance and interfaces, those two topics. If I have a as parent. Let's make that example. Parent, yeah, like so. Let's just do something simple. Public class child, inherited from parent. Like that. So in constellation like this, we can limit our T to only... Actually, let's do like that. Yeah, let's do it like this. What we can do, I can limit T to program. It has to be a program. Oh, sorry, I have to remove that. So program itself works just fine, but something else would not work. Because the float isn't a program, makes sense. We can also change it to parent, this other class down here. And now T can only be a parent. And now it complains because program isn't valid, so let's do that again, just so it compiles at least, like that. That's right, as you see it right now, it's no different than just specifically writing the method for that one type. But once you have inheritance in here, like program inherits from parent, so program is a form of parent, just a bit more. Well, now we can fulfill this condition down here with a program. Because program is a parent. It's not the specific type parent, but it fulfills all the conditions of parent because it inherits all its properties. So this is still fulfilled. And the same goes for interfaces. Interface iParent. If I implement an interface, I can also limit ourselves to that. Same idea, because program fulfills all the conditions, all the requirements an interface has, if you implement it. We can be used in cases where the type parameter is constrained to that interface. And so those are constraints. For a simple case, you might not even need that. But if it's a bit more complex, you might want to change it. And those are the 4 basic constraints that you have in the older language versions. You can limit it to specific class or interface. So everything has to implement those interfaces or inherit from those classes or be those classes themselves. You can limit it to reference types in general, to value types in general, or to reference types that have a parameterless constructor. And in the newer ones, we have a couple of additional constraints that align with some newer language features, which are interesting but not relevant for us right now. Let's keep that up for now. Actually, let's remove that. Because there's something more you can do with generics. Right now we've used generic method, but you can also have generic class or generic interfaces as well. We're gonna try it on a class. Generic class, not actually, let's give it a name, do it like last time, container. So this would be a simple class, public int value, like so, that has single field value. So we can have a container, c equals co container, like that, and c dot value equals 1. Actually, nah, let's not bother. This class container can store now a single integer value. Nothing weird about this. But we can change this to a generic class as well, like so. Again, with the angular brackets directly after the name. And now this fictional data type T doesn't just exist in a single method, but within this entire class. So we can use it for the field, for example. This value is now of type t, whatever we decide t is. Which is pretty cool, allows us to do some really cool stuff, but there's one downside here. This line doesn't work anymore. Because right now we're creating a new container. But container is not an actual class, it's just the template for a class. And the compiler will need to generate the actual classes based on the types we need container to be used for. That means we have to provide the compiler with some indication of what type we want to use for t. And to do that, we have to use these angular brackets in our normal code. Like that, and like that. Which might look a bit ugly, but you get used to it. Now we definitely told the compiler, yes, we want a container specifically for integers. And so that's what the compiler will generate. It will create a container where t is an integer. So if we remove this, compile, everything is just fine. If I didn't provide these angular brackets with the int, we would get this. We require one type argument. We need to tell the system somehow what we're using here. Let's go a bit further. Let's make a constructor, because I don't want to set the value in a second step. I will do that in one go. So we create a constructor, public container. And this part, it's important. This data type t, this fictional type t, exists within the entire class. So I can use that as the argument for our constructor without adding any angular brackets like with the purely generic method we had before. Because we already defined what t is. It's a fictional type that exists only within this class as a reference for the compiler to know where to put which data type. So we do this. And you can just put a 1 in here. Like that. This has a certain consequence though. When the compiler tries to figure out what this container is supposed to be, it now has an indication of what type t has to be. Our container has a constructor that requires an argument with t. And we call the container with one value exactly, lines up with our declaration here, and that value has type int. So it can actually figure out what t is. But that would only apply to this constructor call. In the end, what we have on the left side could be something completely different. You might say, sure, if we create a container here and store it in a container, surely this is also a container for integer types. But it doesn't have to be. There's nothing that fixes it as an int. After all, we could also store integer values on longs, correct? So why should we assume that this container is not some other class that can still store a container? I mean, that might be a far-reaching example because we don't inherit from anything and we don't implement anything, but in theory, this part on the left is removed from the part of the right, on the right. So we have to add int in here, but it should be able to figure out that we mean int on this side. And it doesn't. Is that a new language feature? Okay, I'm kind of confused, because this should have worked. I might get something mixed up here. I was sure it should work. It should work for generic classes, so we go back to public static void method. Let's just call it m. for t, and t integer. Let's leave that empty, just a generic method. If I call that just like so, it should have no problem figuring out what I do. Yeah, in this case it's fine because it knows 1 is an integer and it already applies that. Either that's a new language feature or I'm completely mixing something up here. Well, that's unfortunate. Alright, but you did learn something new. At least for basic generic methods, it can figure that out. For constructors, this is a bit different for some reason. Okay. Sorry. Now, something else interesting happening for generic classes. Static bool. No, it's just called a flag. Whatever. We now have a static boolean in container. So generally, static, if you remember, was a type of value or method that's unique to the class as a whole and not to a specific instance of the class. So this boolean flag only exists once in our entire memory, no matter how many instances of container we build. So we don't need to create an instance to access that. We can just say flag like so. Or at least we would be able to if container was not generic. Keep in mind, what the compiler does is it takes our generic class and it makes a copy and then adapts it to whatever data type we do need at that location. For example, if we need one for string, it will create one for string. And if we need another one for int, it will create another one for int. So in the end, we have two different classes. One that is based on our original class but for strings, and one based on our original definition but for integers. That means we have now two static flags. One for these strings and one for the integers. So up here, I still have to specify what type I have. Do I have the string dot flag, or do I have the int dot flag? And because those are technically two entirely different independent classes, these two flags are independent values. I can set them independently from one another and they don't affect the other, even though we only wrote this down once. And even though this is a specific type, bool, and not just a generic type t, it still is unique to a specific container version. Specific variation of container for a specific type. Which, in my case, was usually good. Like, this is very useful for me in most cases. But maybe you actually do need a single static value across all variations, no matter what generic type it is. In that case, you will have to work around things a bit. Maybe have a parent class that has the static value and then you inherit from that with a generic value, which you can do. Like, let's do it like this. Parent, just a normal class. Nothing special about that, and we can still inherit from here. You could put that up in there. Now the static flag is set to parent, which only exists once. This is an actual class, this only exists once now. So of course in that case you would actually have parent.flag and not container something.flag, but the principle is there. And if we look at the reverse of the situation, if we don't inherit from something, we inherit this container class. Update class specific container. Yeah. we can actually have this inherit from container. But now we have to make a decision. I have a specific container right now, and I wanted to only use one variation of container, so I have to specify that in here. And then I write normal class, and this thing basically works on a variation of container specific to strings. And that's what it inherits from. We could, however, also leave this with a generic parameter if we give the same generic parameter to our specific container. So now our specific container is another generic class that inherits from container, our first generic class. And its version of T is the same as the one that container will use. We could do even more, something I haven't tried before. We can have another generic argument. We can pass the first one to container, and we can public specific value. We have this as a value for specific container. And let's just copy paste. Specific container could be now int string. Int string. Like that. So let's simplify things a bit like that. And c.value would be now integer, and sc.specific value would be a string. Like that. Or I can change this around, make this a bool. Like that. And this one a string. Actually, let's do this. This could be program. This is valid code now. And so you can mix and match and combine a lot of things. And that's generics. There are some special rules you have to think about, because not everything works for every type, and you have to limit your code to things that will work for every type you allow, which in here you can as well limit with just T class, for example. Right. We've limited container to just reference types, so we have to do that in here as well for a specific container. Okay, but yeah, you can still use constraints. And you can let the compiler then take your code as a sort of template to create as many versions of the same code as you need with a different type every single time. You only have to remember that the compiler is actually creating different versions of the same class or method. So there is a separate class for every type of container or specific container. And that means also every static value is actually for every single variation of your class, not just once anymore. And in extreme cases, you might have to look out for memory constraints, because the compiler suddenly has to create hundreds of thousands of classes, which would be a very weird situation, but I had that happen recently. That was... Luckily, we found another way to deal with the situation, but it's where we had to run across the boundary of what the language allows and what the computer can actually handle. Fun times. Anyway, generics. Enough of that. Let's go over to our next topic. I'm gonna write some example. Static. That's just basically the same as I did in the last stream. Well, let's call it ID. Switch ID. is 10 console.write 9. That break, and let's just copy paste that. Let's say 0 is something like that. 5 could be classic one, and let's make a last one catch all. If it doesn't match any of the others, it will be just nothing. Okay, so now I can call do stuff with different IDs. Let's try them all in the same order as we defined them. It's gonna be 5, and the last one, that's -1 maybe. Oh, yeah, my mistake. So now we have the output of several different IDs, let's call it, that do different things. The only annoying part about this kind of stuff is that you have to remember which value corresponds to which action. Right now it's just some simple outputs, but in a larger program you might actually have to simplify certain behavior down to a single value. Like you have a simple list of numbers that have special meanings. Right now it's commands to do something specific based on ID. It could also be the reverse, that something happens and it's condensed down to a single number, like an error code. And if you want to deal with those numbers, well, as a programmer, it's tedious, because you have to always look up a chart which number means, what number to use for which action. And you can do a lot with just commenting, right? You can add comments to here to declare what it's doing, but that's only helpful to the person reading. And the person reading might be someone who has to review your code and then has to check if that actually aligns with what you put in. One way around this, that's like that. I'm just gonna make public static class constants, like that. And we're gonna have a public const int. Let's do it like that. So surprise is gonna be the 10 dots as 0, and hello equals 5. We have just some constants in here, and then up here I can just call constants.surprise. And for this one I use constant.dots. Constants.hello. And for this last one, we'll just leave it at -1. And we can do actually the same in here. So if I want to check this code, I also don't have to look up the values myself. I just refer to these constants in our code. Which also has the added benefit of, if I ever want to change these numbers, I can just do so once. And my entire code will just work. Because no one actually uses these numbers except the program while it's running. The actual code later on, when it's running on the PC, will use a 10, a 0, or a 5. But to the programmers involved in this code, we only see these words. We know exactly what is meant, and we can easily change the actual values the compiler will use for the program later on, without doing anything ourselves. Very convenient, but also a bit limiting. Because first of all, I have to write out a single constant for every single value. And this class constants is now just somewhere in my code. I have this entire class, which is only storing some constant values. It might do something else, but right now it doesn't. And keeping track of everything, it's not the most elegant way to do it. But it's still better than having to look up actual hard-coded values somewhere in a list that you share with your team. In C#, we can do something similar to this concept, but limited to only storing numbers or words. And to make our code a bit easier, we can actually keep everything we've written so far as it is. We only have to change this part down here. The first thing we're going to do is remove this static class, because there's another keyword we can use. You've seen class, and you've seen struct, and you've seen interface. And now you learn about enum. And in enum, we can just... Can I actually... I can do that, can I? Okay, no. Okay, I have to do that by hand. And in enum, I can remove these in front. These are implied. First of all, every value here is always constant. The public is just taken straight from whatever visibility the enum has as a whole. So this accessor is applied to every single value in here. The int is also implied right now, though we can change that actually. And the most important part, we don't use semicolons. In here, we use normal commas, because we just have a list of values. And now that we've changed this code, there's only one detail we have to actually change, this one up here. Because right now, we are not using integer values anymore. This has become a type now. This is basically become a struct. A value type. A valid type we can use instead of integers. This is, under the hood, still an integer as far as the program is concerned, for most things. But it's still slightly different. It has a bit more special meaning. Oh no? Oh, right. Forgot that part. Okay, we'll get to that in a moment. Like that. So I can use these values we defined in our enum, referring to different parts in our code that require specific value during runtime. And what I can do as well now, since nowhere in my code I'm actually referencing a specific value, can skip these assignments completely and just list these names, which works just fine. What happens behind the scenes, the compiler will see that these values don't have a specific value. We didn't give them anything. We didn't say what we want stored in here, which integer value this should be. So the compiler will just start at 0 and give every value in here its own unique integer value with a default value corresponding to its position. It will start at 0, and in the order we provide the words, it will just give every single one number in ascending order. So this is the same as not having anything at all. And sometimes you want just this, where you just have different values, which you don't want to store as actual numbers that you have to look up, but just as a keyword, sort of, like a constant that you can reference everywhere in a code. But what the compiler sees is just, okay, this is a 0. So effectively, I'm just saying 0 up in here, and I'm referring to 0 in here. That's what the compiler will see later on. But we as a programmer have it a bit easier. We can see the word and derive meaning from that. We can also enforce that these enums have to be used for our method. So you can't just have a random number appear, like here, that mixes in with your code. While yes, these are integer values, you can't just use an integer. DoStuff expects a value for this enum constants. So it expects a value that has associations with it. And this random number might be just a result of some calculation that should not be passed onto this method. And this is a way we can catch that early. If a programmer didn't specifically tell us that, yes, this is a value that fits in these definitions, then we don't accept it. Programmer can't do that by forcefully casting that to the other type. Because it is an integer type, you can cast or cast to. And do this. And now it will convert this -1 to a constants. It is not defined in this list, however. It just has the value -1 and it is of the type constants. It is not one of the values that exists within our own definition. That's something to look out for sometimes. Usually you would use these in a switch, that's very common. And then you should be aware that you probably should add a default with maybe an exception. Yep. That tells you that, hey, there's some unknown value that someone gave you. Stuff like that. Oh yeah, like this. You can convert some simple directions, simple arrow codes or whatever into some meaningful words in your program code for your programmers. And there was something else I wanted to discuss about enums. What was it? I forgot something. We don't talk about flags yet. We haven't discussed attributes. That comes later. I forgot something here. Right. I said earlier the public, if we compare to the original public const int sub, the public is based on the accessor for the enum as a whole. The const, that's a given, it always has to be, and the int was implied. I also told you that constants is basically a value type, because it's an enum. All enums are a value type, and they all are integer types actually. And by default, it will use int. So constants is basically an integer. Normal signed integer, int. But you can use other integer types as well. I can inherit from another type. Basic inheritance. I just use a colon in here and then, for example, use short. This is still valid code now. Only those types are now no longer integer values. This ID here is basically a short, just limited to constants with a bit more meaning. I can also specifically call out int as that's what I am, but this is the default anyway, so you don't have to explicitly write it out. We can also go bigger, we can do a long. That's fine. And in some cases, you might want to be a bit more frugal with your memory space and you just want to byte. Have to, of course, be aware of certain issues that might arise because negative values cannot be stored in a byte. So this up here doesn't work anymore. I can do this though. That's just fine. that's Enums. And with that, we have both topics covered. That's actually all I wanted to do on this stream. Since we have a bit of time, right? I started an hour ago, I think. Where's the time? Okay, that's kind of useless stat. Why? It's not giving me the stats. Why is it not giving me? Okay, I have to check that later. Whatever, let's discuss last topic, surprise topic. A fresh topic, this one I didn't discuss last time. Let's... Okay. Since we learned about generics, we can do a cool little thing here. I have some array. Actually, let's repeat our code from earlier. Alright. Let's make it simple. Foo var. The same we had earlier. Public static. Let's go void. Right. And yeah, why not? Let's do it. Let's do generic, why not? T array. That. And then console.write line. It's an array. In array. For each T item in array. Console.write line. Let's use interpolated strings. Personally, I just very much like interpolated strings. If you don't use them in older versions of the language, that's perfectly understandable. If you don't like them there, you have actually a reason at that point, apart from personal reference, because the performance was a bit worse than just having concatenation with plus. Still not the best way to put strings together, by the way, but that's a specific class we have to talk in the future about. Oh dear. Was it? We have a T for our tab and then item like so. New versions of C#, that whole issue with the performance was basically solved. At least this kind of thing is basically the same as if you just had concatenation with string concat or something. It's doing that automatically nowadays. Alright, so that was our old code. Right. Words. Okay, let's see if that worked. Okay, we're back at our old code. Usually when you write a larger program, you don't necessarily have this method right next to the code where you need it. In this case, we have both methods, our main method, which is where we need it, and the write method in the same class. In a larger program, my public class, let's call it helper. Not a good name, but it will do for now. We put it somewhere else. And now I have to actually call it per helper dot write. If I just use write, it doesn't know what to do because write doesn't exist in this class. We have to specify where to find the method, or if there are several versions of it, from which class we want to take it. Alright, so that works, but not always convenient to write out like this. Because you have to call a method and you have to provide words. There is something cool you can do in C# where, well, I'm just calling it out like what it is, where you extend the functionalities of a specific instance of another class by writing static methods that work with that class. When introduced inheritance, inheriting from other classes, I use the term extension a lot. Extending something. I'm extending the functionality of that class. And in that case, it was just a figure of speech, just a way to explain to you the child class has all the properties of the parent and some of its own stuff. So it's making the list of things it can do bigger. It's extending it. In this case, we're talking about actual extensions. And extensions only work for methods. So we have extension methods. And the way that works is we write a method, like we have here, and we let the compiler know that this is supposed to be an extension of what something else can do. Treat it as if it was part of that other class's set of existing methods. And right now we want to extend the abilities of an array of t. We could also limit this to just string. Let's do that maybe for now. We have a specific method, not generic anymore, for string arrays. Code still works, of course. And we want string arrays to have inherently this functionality of writing out the content. Instead of writing out the whole, hey, go to class helper and call the static method write in that and pass onto that this string array that we have. We can change this code to do this. We take words, our string array, and just write it out. We pretend that write is a method of string array. Like this entire thing, not strings, but string array. We pretend like this has a method we can call called write. It doesn't actually have that. The compiler is very much aware of this not being a method in string array. That's important. This isn't actually a method in there, but we can write it out as is, and the compiler will just do the necessary changes for us. But we as a programmer can use it as if it had that method. And to tell the compiler that we can do that, we have to make a little change in the arguments in write. We add a keyword in front, and it's one you've seen before. And this is one of the other uses this keyword has. This. You might remember it from using it to make ambiguous references to variables a bit easier. If you use a variable inside a class that also has that same name for property or field, and you've seen it to reference another constructor in the same class from one constructor. So if one constructor in a class calls another in the same class just with some additional arguments or less arguments. This is a third use for it. This lets the compiler know that this method, which we can still use as normal, so just to be clear, we can still use helper.write just like before. This is still valid. The compiler can just ignore this and treat it as the normal method. Besides this, it will also accept us to treat this method as an extension of string array. So if we use a string array somewhere and we just put a dot after this and then write, the compiler will also check, are there any methods that are available in this context here that have this signature, that are called write, and that have a this before a string array. And if so, it will call that method. It will simply convert this call into this call and then use that. So this is what we write, and this is what the compiler will turn that into for the program. Both will just end up in the exact same thing. There are some limits though. Besides this keyword, there's another thing we have to change. This class right now can be instantiated. We can actually create an instance of helper. And that's not allowed. We have to make the entire class static as well. So this class can only have static fields, static properties, and static methods. There are no instances of helper anywhere in your program. That's not possible anymore. Now, it will actually accept this. Honestly, I'm not too sure about the details why that is a requirement. I'm sure there are very good reasons. I simply do not know them. At least I can't think of a reason why this would not work. I mean, there are things you have to look out for in general, regardless of if the class is static or not. It might be something to do with the way statics are different from instance-based method inside the actual runtime, like how the .NET runtime handles that situation. I don't know. Be interesting to know, actually. I have to look that up. Probably find a large article by Eric Lippert about what a pain that was to implement at all, and something like that. Well, I'll look that up later. Anyway, this is what we can do. We can use a method and add something to it. We can do that for other types as well. For example, public static. Let's actually do this. Int negate. And then we do this int value. Because we can do this extension also for other types that are value types. Like this can apply to structs as well, and even some already predefined value types like int. You can of course have return values as well, so return minus value. So we can do helper int a equals 1, and then int b equals helper dot negate a. That works, but we can also do a dot negate. I mean, you can't see the output right now, but this works. And you don't actually have to put this after a variable. I can also do this, as weird as that looks. Dot operation on a number, which works in general, by the way. Like there are other methods you can call like this as well. For example, the toString that I think we've talked about at one point. Like there are other methods that already exist that you can call like that. So it's not too strange that we can call extension methods that we write ourselves on that. Oh yeah. That was it for today. For real now, we have generics, generic methods, and generic classes. We have enums. And we now have extension methods. I now have to look up still how to set up very nice isolated sandbox, and where I can demonstrate how to set up a dev environment and where we can work in the future. Which turns out to be quite a pain. Streaming can be very annoying sometimes. Anyway, yeah, maybe have some fun with these different functionalities. Maybe they solve some issues you've had when you tried programming so far. Take your first steps. And see you next time.